Assalamualaikum and hi. Now let's get started with our first tutorial questions, which is question 3.19. So it says that a mixture consists of 10 mole percent of ethyl alcohol, 75 mole percent of ethyl acetate, and 15 mole percent of acetic acid. So it asks you to calculate the mass fractions of each compound and what is the average molecular weight of the mixture, as well as what would be the mass in kilogram of the sample containing 25 kilomole of ethyl acetate. So you know from the question it says that a mixture consists of 10 mole percent of ethyl acetate, which is 75 mole percent of ethyl acetate, and 15 mole percent of acetic acid. Okay, so to calculate the mass fractions, you need to know what is the mass of each species, and also the total mass of this species in the mixture. So mass fractions is actually defined as the compositions of the mixture of the substance, which include this total of each compound. Okay, so it often denoted as X A equal to mass of A over total mass. Which is in kilogram per A, gram per total, or gram per A of in gram total, or in pound mass of A within pound mass of the total. So A is actually you can which is the species, which is the compound from the mixture. So now you have to know and to calculate the mass of this each compound. So you can directly let's calculate the mass fractions of each compound. So now you can calculate the mass of ethyl alcohol. Okay, you can assume basis, which is 100 mole of mixture. Total of this. So now it is 10 mole of ethyl alcohol. You have to times with the ethyl alcohol molecular weight, which is 46.7 gram C2H5OH in mole. So now you get the mass of ethyl alcohol in the mixture, which is 461 gram of ethyl alcohol. Okay, next, the mass for ethyl acetate. So it is 75 mole of ethyl acetate. Times with its molecular weight, which is 88.1 gram of ethyl acetate in 1 mole. Now you get the mass for ethyl acetate is 6608 gram of ethyl acetate. And the last one, which is acetic acid. So it is 15 mole of acetic acid times with its molecular weight, which is 60.05 gram of acetic in 1 mole. So you get the final answer is 901 gram of acetic acid in the mixture. Okay, now you already know what is the mass of each compound in the mixture. So from the formula you know that the mass fraction is the mass of each compound in divided by the total mass of the compound within the mixture. So now you can calculate the total mass of each compound, added it all together, so you get 7970 gram of mixture consisting of the mass of all of this compound. Now you can calculate the mass fractions of each compound. For ethyl alcohol, so the mass of ethyl alcohol is 461 gram divided by 7970 gram of mixture. Now you get 0.0578 gram of ethyl alcohol in gram of mixture. For ethyl acetate, it has 6608 gram divided by 7970 gram mixture. 0.8291 gram of ethyl acetate in gram of mixture. And for the last compound, which is the acetic acid, we have 901 gram over 7970 gram of mixture. 0.13 gram of acetic acid in the gram of mixture. Okay, now it asks you to calculate the average molecular weight of the mixture. So the molecular weight is actually equal to the overall total mass divided by total mole in the mixture. Now you get the total mass of the mixture is 7970 gram divided by 100 mole of the sample, so you get 79.7 gram per mole. So this is the average molecular weight. So you get the average molecular weight of the mixture is 79.7 gram per mole. You can use this to calculate the last part, which is the mass of a sample which contains 25 kilomole of ethyl acetate in kilogram. So this means that the mass of the mixture, let's say it consists of 25 kilomole of ethyl acetate. So calculate the mass. 25 kilomole of ethyl acetate divided by the mole of 75 mole of ethyl acetate in 1 mole, but in this case you can use it in kilomole. 100 kilomole of mixture and times with this average molecular weight. which is 79.7 kilogram of mixture in 1 kilomole of mixture. So you will get the kilogram of mixture in that contain of 25 kilomole of active state, which is 2,660 kilogram of mixture. Okay, let's go to the last questions for question 3.23. So it says that the mixture of methane and air is capable of being ignited only if the mole percent of methane is between 5% and 50%. So mixture of containing 9 mole percent methane in air flowing at the rate of 700 kg per hour is to be diluted with pure air to reduce the methane concentration to the lower flammability limit. So calculate the required flow rate of air in mole per hour and the percent by mass of oxygen in the product gas. So there is a note, so you can take air to consist of 21% mole percent of oxygen and 79% of nitrogen, and use this average molecular weight of 29. So first of all, what you need to do is you need to extract all the information from the questions. So here it says that the methane is only capable to be ignited if the mole percent of methane is between this value. Okay, you can illustrate or extract the data in these missions. So this is the methane flowing in and also the air, and this is the product coming out. Okay, so it says from the questions that the methane is 0.09 mole and the rest will be the mole for air. So methane is flowing at a rate of 700 kg per hour, and we don't know what is the flow rate of air. Now for the product, what you need to know is the mass of oxygen in the product, the percent by mass of oxygen in the product. So here it says that to actually reduce the methane concentrations to the lower flammability limit, so you have to dilute it with pure air. Okay. So now, first thing what you need to do is you have to calculate the average molecular weight of the mixture using these equations, which is the ratio of the mass of the sample of the mixture to the numbers of the moles of all species in the sample, which is for this case it's methane and also the air. So you know that the methane has 0.09 mole. Now you have to times with molecular weight of methane, which is 60.04, and you have to also know the molecular weight for air, which is 29 from the equations. Now you can times with the molecular weight of methane, 16.04 gram per mole, as with 0.91 mole air times with 29 gram per mole. So you get the final answer. The average molecular weight of the mixture is 27.83 gram per mole. Okay. So now you have this value, so you can use this value to convert the flow rate of methane to kilomole per hour. So you have 700 kilogram of methane times with 8 mole in 1 mole of mixture, but in this case it is in use in kilomole because of this kilogram, and times with divided by this value, by this average molecular weight in kilogram per kilomole. So now you get the rate of methane in molar, which is 2.264 kilomole methane per hour. Then you can use this value to calculate how much the molar flow rate of air. So this 2.264 kilomole of methane times with 0.91 kilomole of air in 0.09 kilomole of methane. So you can eliminate this, so you get that the kilomole of air is 22.89 kilomole air per hour. Okay. Next, it is said that for methane to be ignited, so the mole percent of methane must be in between 5% to 50%. So we take the minimum value, which is about 5% of methane, and we calculate how much or how many mole of air per hour is needed for this 5% of methane. So you can calculate from this molar flow rate of methane, which is 2.24 kilomole of methane per hour. You can times with 0.95 kilomole of air, which comes from 5% of methane, and the rest is 0.05% of methane. How you get 33.01 kilomole of air per hour. So this is how much you need to dilute air so that it is so that it can reduce the methane concentration to lower flammability limit as said in the questions. So now you can calculate how much the dilution of air is actually required. Which is, you can use this value minus this value, so you get the mole of air or molar flow rate of air required for dilutions. So here there's 43.05 kilomole air minus with 22.89 kilomole of air per hour. So you will get 20.200 kilomole air per hour, or 20,200 kilomole per air per hour of air per hour. Sorry, this is in mole per Now we go to the last part, which is ask you to calculate the percent of biomass of oxygen in the product gas. So now you have the mass flow rate for methane, which is 700 kg per hour. You just need to know what is the mass flow rate for air, and we added it together. So the product gas consists of 700 kg per hour of methane plus with 20.20 kilomole air per hour times with molecular weight of air, which is 29 kg of air per kilomole of air. So now you get the product gas consists of the mixture of 1286 kg per hour. So now you get this information, so you can calculate how much the oxygen is in the product gas. So here the flow rate of this dilution is 43.01 kilomole of air per hour times with the molar of oxygen, which is 21 mole percent, so it is in 0.21 kilomole of oxygen over the overall 1 kilomole of air from 1 kilomole of air, and times with the molecular weight of oxygen, which is 32 kilogram of oxygen in 1 kilomole of oxygen, and divided by this total flow rate, which is 1286 kilogram per hour, and you get the final answer, which is the percent biomass of oxygen in the product is 0.255 kilogram of oxygen per kilogram of the mixture.